Okay, who is ready? Okay, this part is going to be easier than HBase. So you can now sit back and enjoy maybe a bit more, even though it's very enjoyable to see the HBase architecture, of course, the way that it's all batch processed. So welcome back. Now we are going to talk about data modeling. So it's again about data independence and logical aspects of the data we're manipulating. You remember that this is the stack that we are building in this lecture. And we've already covered a lot of that, right? So we have the storage, the encoding, the syntax, XML, JSON, CSV, YAML, data models. We've seen a little bit, well, HBase, I'm not sure if we would call it a high-level data model. You could still consider it has a tabular structure. So we are going to look at these two levels, basically, data models and validation. And in 2 weeks, processing and then indexing and so on, we'll cover a bit later. So this is where we are at now. But before we do that, I want to take a small break to circle back and look at what we've learned on the very high level, the design principles so far of big data. So the first thing that is very important, and that's the way that the technologies were designed, is to learn from the past. These technologies that were built, S3, HDFS, Dynamo, HBase, and so on, they didn't reinvent the wheel from the very beginning. That actually builds, that's what we call building on the shoulder of giants, right? So there's been existing technologies before, general principles like modularization, data independence, and so on, building in layers. Learning from the past also means not repeating the mistakes. A story that I like to tell is that of JSON versus XML, is that for historical reasons, the XML ecosystem is older than that of JSON. It's actually complete and very robust to the point that it's enterprise ready and governments and companies trust XML technologies a lot. JSON is a bit younger, and it's something that could have maybe have been better if we had developed the JSON technologies learning from the XML technologies, in the sense that there was a bit of pushback against XML at the beginning because XML is very complex. And it means that we reinvented and went through solving the same problems with JSON that we had solved with XML. An example is that we had XML schema, now we have JSON schema. We had namespaces, now people try to also reintroduce them in JSON. We have query languages that at first didn't exist for JSON, but then there was XQuery for XML. Now we have 30 query languages for JSON, and so on, right? So basically, at first, there was the belief that JSON was so simple that you don't need to look at XML, you just redo things in a simpler way, only to rediscover that actually all the ecosystem that has been built around XML also makes sense for JSON, just of course adapted to the JSON data model. So this is the importance of learning from the past, because if you can learn, you don't repeat the same mistakes, and you're much quicker on developing the technologies. All right. Second, keep the design simple. You remember that in S3 HDFS, the logical model is very simple. In S3, you just have bucket IDs, object IDs associated with objects. In HDFS, you just have a hierarchy of directories and files that have blocks, and that's it, right? So keeping things simple is also a very, very important piece of philosophy for the design. Also because our brains are limited as humans, and we need to have simple and understandable abstraction primitives to work with. Something related to keeping things simple is to have a modular architecture where you design the layers one by one. It's a bit the question that had been asked earlier about the pieces of the puzzle with Hive and Phoenix and so on. And it's because of this that we can do this, because you keep things simple at every layer, and then you pile up the layer, but every layer in itself is simple to understand. And by piling them up on top of each other, you build a complex and robust system. So the modularization of the architecture. Then something else that we learned is that when we look at very, very large scales and you deal with tens of thousands of machines, you want some homogeneity in the data, just like you spread blocks all over the data center. The idea of a block is homogeneous. All the blocks are interchangeable in terms of storage, right? So you just spread them all over the data center, and it is because of this homogeneity that you're able to do this. The same for the values in DynamoDB, the regions in HBase that all look alike. So this is why you can spread them across different region servers. So homogeneity in the large, but heterogeneity at the small scales of the data. This is how you accommodate for the real world, right? Where the data might not be in highest normal form and fully structured, and you might have a lot of heterogeneity, but that's what you do at the level of, for example, at the level of single objects, of single documents, and that's also a very important aspect in that is present in big data, a bit less in the older relational database management systems, right? So there is this contrast between at very large levels, it all feels homogeneous, and when you zoom in, then you see the heterogeneity of the values and of the documents. Number 6, that's data independence. It's the idea that you separate the physical implementation from the abstract logical model, and that I did every week. I did it for S3. Well, for S3, I did not even give you a physical implementation because we don't know. I did it for HDFS, first the logical model, then the implementation. I did it for HBase, first the logical model, then the implementation, and I do the same for MapReduce, Spark, and so on, right? So you have to have this boundary between the physical implementation and the abstract logical model, because this is how you keep your sanity as a computer scientist, right? You have a very well-defined logical model that you interact with, separated from the physical implementation, and you keep optimizing the physical implementation without modifying the logical model. Okay, that's number 6. Number 7 is that in big data, we love to shard the data, to partition the data, because this is how we build things that are bigger than single machines, right? So we partition the data. We did it with files in HDFS because we partitioned them in blocks. We did it with HBase because we partitioned the row IDs into regions, and we even partitioned each region into the multiple column families that it's made of, right, the stores. So partitions are everywhere. We'll see them again with MapReduce, with Spark, and so on. We just keep working with partitions, right? They have many names. We call them blocks, chunks, splits, partitions, shards. There's many names for that, but it's all the same idea, right? Divide and conquer. Then we don't only partition the data, we also replicate it. It means that every one of these partitions, when it's physical storage, will be replicated. That's what happens when we replicate the HDFS blocks at multiple places. Of course, that doesn't necessarily apply to the logical partitions. The region servers, for example, there's only one of them for each region. That's because we don't lose data with that. We can only lose data if we don't replicate at the physical level. Okay? So that's number 8. We shard and we replicate. The two go hand in hand, just like homogeneity in the large, heterogeneity in the small. They go hand in hand. Right, so shard and replicate. Then we have number 9, which is the idea that we buy tens of thousands of machines, even millions of machines, if you're building a spanner, that are just piled up on top of each other in racks, assembled in data centers, assembled in availability zones, assembled in regions, and then you get the whole planet, right? There's even people working on something called interplanetary file system, maybe a bit ahead of our times, but this is something that also makes sense from an engineering perspective. Okay, so all these machines, number 9, and number 10 is that we batch process. The idea of batch processing has to do with these partitions. It's the idea that we think and read and write at the partition level. For example, for the blocks in HDFS, we read or write single blocks at the same time, right? And you saw it in action with HBase because we do not write something to HDFS every time a value is inserted. That would be very inefficient. You would have a latency every time a small value is inserted. Instead, you accumulate this into memory, into the mem store. You just keep it pending. You write it in a write-ahead log. And when the memory is full, you write as a single go, you flush it and write one H file. This is batch processing. You batch the persistence of all the key values by doing it in batches, all at the same time, and then you compact and you split and so on. So that's the secret, the batch processing, on how you can build a system that has low latency on top of a system that has high latency, right? That's how HBase builds on top of HDFS. Who has the feeling they now have an intuition of why we manage to build low latency HBase on top of high latency HDFS thanks to this flush compact split? Who has an intuition? Right. Okay. Who doesn't yet have the intuition? Some of you, right? So take the time to read the textbook. If you still don't have the intuition, let's say in 2 weeks, write me an email. I can explain it again, right? If anything is unclear. This is a very important aspect of the lecture, this idea of batch processing, right? We'll see it also in action. So I'll come back to it with MapReduce and so on. It's the same idea of batch processing the data, right? Maybe I can find a real life example. You know, in real life, when you work on something and then you need to work on something else, your brain needs to adapt. That's called the context switch, right? And who has ever noticed that on the same day, you had to do a lot of small different tasks and it was very tiring for your brain just because you needed to switch all the time? Who already experienced this, right? So this is because of the latency. There is latency to move from one task to another, right? That's basically HDFS, right? One block to the other, it takes a lot of time. Now, who has already organized their day or their week by grouping similar tasks together, or maybe doing tasks that require input from the same location or output to the same location, and you notice that it was less tiring and more efficient, right? Like wedding invitations, for example. You just gather your friends and then you just write all of the cards or assemble all of the cards in batches, right? 100 at the time. That's an example of batch processing, right? So this is the spirit. That's exactly the same intuition. That's also the same reason why we prefer to process thousands or tens of thousands of records or hundreds of thousands of records at the same time rather than one by one, right? Who has a better intuition now? Okay, very good. All right, so that is batch processing. So as I said, we are done with this, and now we are at the data models and soon validation level today. You remember that 2 weeks ago, I showed you XML and JSON documents, and I asked who sees a tree. You remember that, right? And some of you saw a tree, and some others did not see a tree. Well, today I'm going to try to make you all see the tree when I show you XML and JSON. I think CSV is solved, right? Who sees a table when you look at a CSV file, right? This one is easier. So this is CSV, and that's the syntax. So on the bottom, that's the syntax, and on top you have the table. Okay. So small reminder for JSON, we have 6 building blocks syntactically. We have strings, numbers, booleans, null, and we have objects and arrays, right? That's from 2 weeks ago. Here's a JSON document. Who sees a tree? Raise your hand. Well visible. Who sees a tree? Okay. Who doesn't see a tree yet? Ah, that's better. It has improved. Maybe the experience with the exercises helped a little bit. Then let's ask, does anybody volunteer to explain to me how that tree looks like? Like what is the root? What are the children of the root and so on? What are the leaves? Does anybody want to volunteer? Yeah, I see a raised hand over there. Maybe we can give the, on the left. Yeah, oh, not in a single small hops. Yeah. Yeah, over there. Yeah. Yeah, there you go.
Okay, so I'd say that the root is the whole object, and then we've got 3 branches that we can label with the keys, so foo and bar. And then foo has got like the branch just ends in a Boolean object that has the value true. And then bar has like two branches that we can identify with numbers, maybe the indices of the two sub-objects. So, and then the first sub-object that's got one branch labeled foo bar with the value foo, and another the bar array as one branch with index 2 and with the value null.
All right, perfect. I have the visual for what you've just said. Actually, I realized I could have clicked as you were saying it. There you go, right? Who agrees with this? Who sees the tree now? Okay, this is the tree. All right. So as you notice, thank you very much. Excellent. As you notice, we have the JSON values, the object, the Boolean, the array, an object, and a null. And I use the different shape for the keys because the keys are like labels on the edge that connects the values together, right? So I put them as in an elliptic fashion. Okay. Oh, there was one missing. We have also a foo bar and foo. Okay. This, in fact, what you have on the right, do you agree it could be a memory representation of the document after you parsed it? Who agrees? Awesome. So now, 2 words for you. To parse means you read that text and create, oh, wrong direction. You read that text and you create the memory representation. That's called parsing, right? And then you work, of course, with the memory representation. At that point, the syntax is irrelevant, where it came from. Do you know what we call the other direction when you take the memory representation? I think I mirrored, that's why I'm having trouble showing things. There's a mirror in the video. Anyway, going from here back to here. Does anybody know how it's called? The contrary of parsing. Yes? Serialization, exactly, that's the serialization. Serialization means you take the tree and you write back JSON. Of course, you could also serialize to something else. You could serialize to YAML or to XML and so on. So remember these 2 words, to parse, to serialize. They are opposites of each other. Okay? And basically, this idea of parsing and serializing means moving between the physical representation as text in a file all the way to a tree-based memory representation. The edges that you see here are actual memory pointers, right? So it's very efficient. Okay, it's another document, by the way. Who sees the tree? Okay, very good. That's the tree here that corresponds to that document. Who sees the tree with XML? I even drew it on the screen. Who doesn't see the tree with XML yet? Okay, some of you will draw one, right? But as an example, this is an XML document, and that is the associated tree. We have A at the root, 2 child elements. D has a child attribute here, E associated with F, and C has as children text, a child element which itself has child text, and then and that's it. Yeah. So that's the XML tree. JSON and XML is really the same. These are just 2 syntaxes for trees. That's very important to remember. It's denormalized data, and it doesn't matter if you use one or if you use the other. There are minor differences typically in the representation. I told you that in JSON, typically the keys, so the names with which you associate the values in an object are labels on the edges of the graph of the tree, right? So they are here. In XML, we do it differently. In XML, the labels are on the nodes themselves of the tree. A simple way of saying that is that in XML, an element knows its name. An attribute knows its name. In JSON, an object doesn't know what key it's associated with in the outer object, because that's earlier on the edge. Who understands this? Right? So basically what it means is that if you hold an object in memory that is an XML element, you can ask what's its name, and you will get an answer. You hold an attribute, you can ask what's its name, you're going to get an answer. If you hold a JSON object, for example, you hold this object right here, and you ask for its name, you don't know, because the name is not in here. It's earlier on the edge, but you don't go back right? So this is why here it's a different architecture. It's important conceptually because it does make a difference a little bit in the design of the query languages, right? But that's just so you know that there is this little difference between the two. So now, drawing the tree for JSON was pretty straightforward. We'll also do it for XML now, but you'll see it's actually not so complicated. Technically, from a specification perspective, there is a specification for the syntax of XML. There is a specification for the syntax of JSON. XML is actually so complex that there is another specification for the data model of XML, another one, and that is called the XML information set. It's only a fancy sounding name that just means the data model for XML, right? That's what it means. By the way, information set is too long, so we just say XML info sets when we speak quickly. So the information set, the info set is just the name of the tree, basically the description of the tree. So I'm going to take this as an example. Who sees the tree here? Okay, many of you. Who doesn't see it yet? Okay, let's go through it. So first, I'm going to tell you what nodes we have in our tree. So in JSON, we have 6 of them. In XML, I'm going to simplify. There's technically 11 of them. I'm only going to show you 4. Don't worry about the rest. First, it's easy to look them up if you need it one day. And second, they are less used. So documents, elements, attributes, and text characters. So this is the 4 kinds of nodes. The document node is just the root. It's the top level. You just have one. It's called the documents information item. Again, information item is just a fancy sounding word for node. I could also just say node, right? Document node. But in that standard, instead of saying document nodes, they say document information item. So don't worry, it's just terminology. So the document node, document information item, has children. It's an element, that's the metadata element, that's the children of the document node. And it says version 1.0 because you see it in here, it says version 1.0. So you see that in my data model, in my XML info set, every node that is in the tree, every one of these nodes has some associated properties, right? So the document has a children property and a version. The children property, in fact, is a pointer to another node, right? Who is still with me? Right? Then we have the element information item. It has the local name metadata. Its children are title and publisher, right? So metadata, 2 children here and here. It doesn't have any attributes, you agree? And the parent, because in XML we have a back pointer to the parent, points back to the document information item. Who's with me? Right? I'm going quick over that, right? You're computer scientists. Next one, title. So that's the node corresponding to this element right here. Its name is title. The children of that node, well, look at it. Title, it only has text between the tags. So it only has as a child the text information item containing this text right there, systems group. It has 2 attributes. You agree? 2 attributes right here that I put here and here that are other nodes. And it has the parent. So again, title points back to the parent. Title points back to its parent, metadata. Who is with me? Next one. Publisher. The name is publisher. It has children. Yes, it has ETH Zurich. That's text. It doesn't have any attributes, right? That doesn't have any attributes here. And it points back to metadata, right? Publisher points back to the parent metadata. Who is with me? Okay, let's move on. Attributes now. So the next node is an attribute node, an attribute information item. That's the one right here, right? Year equals 2025. So now the properties of an attribute node are different. You still have a name, that's year. You have a normalized value, that's 2025. Why normalized? Because there might be extra spaces at the beginning or at the end that we just remove. There's a bit of cleanup that is done when we generate the memory representation. So that's why we say normalized. But that's the value, right? Year 2025, year 2025. And we have a back pointer to the parent, which for some reason they don't call parent, they just say owner element. That's really the same thing. So it points back to title. So you see in XML, you can go back to the parents. You can go up in the tree. The other attribute looks the same, except that instead of year 2025, it's language EN. Who is still with me? Right, so I've done the documents, the elements, the attributes, and text now. Text, so it's made of characters. So we have, it's really like SYSTEMS space GROUP, right? That's just what you have here. And then the owner element of that text is title. And again, text here, ETH Zurich, ETH space ZURICH, with the owner element publisher. I insist, this is just text. There is no type in here. Even if it's digits, we don't care, it's still text. There's no notion of integer or double or date or anything. We just have text, periods, right? And basically what that gives us, all of this boring thing, it's in fact something we can put back into a tree just by looking at the children properties and parent properties, we get that back. Who agrees? Right? Awesome. So that's how we specify a data model. We have nodes, they're assembled in a tree, and the nodes have properties, and you have a specification that tells you what properties are there and how you can build a tree out of the text. And there's another specification who says how out of the tree you can regenerate the text, serialize it back to text, right? Who is with me? All right, who is bored? Who finds it too slow? Who finds it easier than HBase? It is easier than HBase, right? Okay, but we need to rest our brains a little bit, right? We cannot just do very complex lectures every week. Okay, so what have we done? We have seen that when we are able to say that an XML or a JSON document is well-formed, we can parse it into a memory data structure that in the case of XML and JSON is a tree. And there are specifications that define how the trees look like. It's called the data model, and it specifies the nodes and the edges and what properties the nodes have, and so on. That is half of the story to do that, to parse it into a memory representation. Why is it half of the story? Because we don't have the types yet. That's why it's only half of the story, at least in XML. In JSON, you could say, okay, we have the types, but look at what types we have, just 4 of them, string, number, Boolean, null. So that doesn't bring us very far. So we still have a bit of work to do to have a richer type system. Which brings us to validation. You remember, because I think there was also questions that were asked about it, because you're very clever, you already asked the questions very early. I told you that when I give you a text document and I ask you, is it JSON or XML, do you remember the adjective that I told you to use? I reused it a minute ago. I told you, do not say valid, say well-formed. Excellent, well-formed. So well-formed means you're able to parse it and generate a tree. Well, now I'm going to explain to you what valid means. Valid is the next step after well-formedness. It occurs after you have successfully parsed it into a memory tree representation. Then you can validate it. So it means that it's the decision tree, very fancy. That's the only machine learning I have in the lecture, if you can call that machine learning. But anyway, either it's not well-formed and it stops here, you cannot even parse it to memory, or you can parse it into memory. And then the next question is it valid or is it not valid? And if it is valid, that's where you get a lot of types and a type system and so on. Very good news, because that's really a practical thing. Who downloaded Oxygen? Okay, you should download Oxygen. It's very good to play with. In Oxygen, it's like Matrix. You have the red and the blue buttons. Of course, in every version, it becomes different. But the blue, normally, that doesn't change. The blue, if you click on it, tells you about the well-formedness. And the red tells you about validation. And you probably noticed if you try to just click on the red button, it doesn't tell you anything. It just complains that you didn't tell it what schema you want to use to validate. Because that's the difference. Well-formedness is yes, no. For validation, you need a schema. So we have schemas, schema languages to define what it means for a document to be valid. Right? So I really encourage you to try this, to play with Oxygen. It's free. You can download it from the IT shop. It can be useful also for later in your project if you ever need that. There's a lot of functionality, can connect to relational databases and so on. Okay. Before I go into the how we validate documents, I need to tell you one more word. So there's well-formedness, there's validation, and there is annotation. Annotation. It's subtle. People confuse them, and sometimes they use validation even though they should say annotation. So it's a bit confused. Validation is just a yes/no. It's just a yes/no. Is it valid or is it not valid? Period. Annotation means that if it is valid, you change a bit the memory representation to take into account what you've validated. Example, you have an XML document or even a JSON document that has text or a string in the case of JSON, and the text says 2025-10-21. That's text, right? But maybe when you validate it, your schema is going to say you expect a date in the ISO 8601 format, which is a standard for dates. And so if the text is made of 4 digits, -2 digits, -2 digits, then it's valid. But then what happens is that you're not going to keep the text in memory. Doesn't make any sense, it's not efficient. You know it's a date. So what are you going to do in your memory? You're going to remove that text and replace it with a date structure that has a year, a month, and a day, right? An actual representation for a date. That's what annotation means. You're going to do the same with numbers. You're going to have a double instead of the original scientific notation and so on. So you replace the texts and the strings and the literals with actual typed values in whatever programming language you're using. Could be Java, Python, or whatever language. But you've enriched the memory representation with typed values. Who understands that annotation? Awesome. So it means that a schema language doesn't just say yes, no, it also optimizes your memory structure with the actual typed values of your system. So you see now we're far away from the syntax, right? We are far away from having parsed the documents. I have a few minutes left, so I'll leave for tomorrow the introduction to the schema language maybe, but what I can tell you is on the intuition on a high level, what do you validate actually with a schema? A single document? Well, yes, maybe when you learn the schema, you validate a single document. In real life, you will rarely validate just one document. You will validate 1 million documents. You will have some data sets that has 1 million JSON documents, and you're going to ask, are these 1 million documents valid against some schema? Or you have 1 million XML documents or 1 billion XML documents, and you will ask, are they all valid according to a schema? And that's the power of NoSQL or big data, is that you can perfectly have data without a schema. You can have a huge, messy collection of JSON documents that all look different, like you just represented on an abstract fashion on the left. That's not modern art, it's just a heterogeneous collection. And the spirit is that when you have a schema, then all these documents should look alike. They have the same fields, the same types, and so on. So you basically clean up the data and prepare it for machine learning, for example, if you need structured data. That is a real difference with a system like PostgreSQL or relational data management systems. You remember that if you want to have data in PostgreSQL, you have to start with create table and a schema. You start with that. You cannot just put data in PostgreSQL without having first defined a schema. But in XML and JSON or NoSQL, it's the opposite. You can just put the data in there. You can put it on the data lake as a JSON lines file, for example. Doesn't matter if it's not valid, just needs to be well-formed. And the schema comes later. You can later try to validate it against the schema and then have more efficient in-memory representations. That is the idea. And once you have a schema, the size of the data in memory will be less. You can compact it because you, for example, you don't need to repeat the keys in every record. It's more efficient. And then you can save it back to disk with a format like Parquet, which is more efficient to read. So this is basically the direction in which we are going. Okay, so that's an example of a messy document, very messy. I have an array with all kinds of values in there. I have an array with even a nested array. So there's no schema in there, right? Who feels that this has more structure, especially here the array has objects that look a bit alike, right? Who sees that these two are a bit similar, right? So this is to give you an intuition. This is the sort of thing that you can define a schema for. You can say that A is an integer and B is a Boolean and C is an array of objects that has foo and bar. Bar is optional, right? But foo is required. Foo is a string. Bar is an array of integers. Who agrees with that? That was a schema, what I've just described, right? And so tomorrow I will teach you how you can define schemas like that. So I'll first start tomorrow with very generic considerations on type systems, and then I'll teach you schema languages. Thank you very much, and see you tomorrow at 9 a.m.